Welcome to the lab, and we are going to do a walkthrough past one instrument and towards a very special instrument that is going to be doing a zero-angle depolarized measurement of cellulose nanocrystals in suspension. So the instrument we're walking past now is a conventional dynamic light scattering spectrophotometer. And there is its correlator screen. Here is where the action begins, really with this laser at the back. Actually, we'll probably mostly use this smaller laser. It's called the obus that you can see there. And that light goes in a normal experiment into that big cylindrical center, and a cell is put in just like that. It's no big deal to put them in. And then it's scattered off at some angle, currently about 25 degrees of scattering angle. And a largish detector, a very good one, but it's large, and they still sell these, but most people go with the smaller detector now. This one works as well as any, but only one angle at a time. Over here is the experiment that we're going to run today. This is a zero-angle depolarized setup, and you can see that there's a laser aiming at a sample. And its detector is clear at the back, and it really is zero angle, and you could wonder why the detector isn't being blown up and destroyed by the laser. And the answer to that is that we have crossed polars placed in this experiment, and you can see them there. The little first thing after the laser that you see is a lens assembly, and that is aimed to the center. And then the next thing that you see coming in the direction from left to right, the next thing that you see is the vertical polarizer. Now, the laser is already vertically polarized, but it only has something like 100:1 polarization purity. So this polarizer that's after that is called a nicol prism, and it cleans up the residual horizontal component, and now it is fully vertically polarized. And then you'll see we have here the sample itself is held, in this case, in a square fluorimeter cuvette, and the beam comes into it. You can see the scattering from the sample as we go through here. Okay, you can see pretty clearly. And then there is a crossed polarizer, and the alignment scheme is to set that thing to horizontal first, and that's the whole trick to doing this, is to get that one horizontal. And that's a long explanation. We aren't going to talk about that. And then after that, we have the detector, the same as before. Okay. And one thing to notice about this is that there's nothing except the sample in between the two polarizers. The lens, there's a lens on the left, then the polarizer, then the sample, then a lens on the right, and then the detector lens. But between the sample and between the two polarizers is just the sample. Now, it turns out that these square fluorimeter cuvettes tend to be a little bit birefringent. And in this case, that provides a certain amount of light that is horizontally polarized, which is going to mix with the actual scattered light. So we'll have light that is generated basically by the glass in the cuvette mixing with the scattered light and depolarized scattered light, which is probably a pretty weak signal. Currently, the signal is going to the detector. If I was to lift this up, then the signal would go to the eyepiece here, and you're going to have to trust me on this. You could look in there now with your eye and not ruin your eye, because the detector, the polarizers are capturing all of it. The amount of depolarized signal is small. The amount of birefringent light generated by the fluorimeter cuvette is fairly small, although it's much greater than the scattered light. And the two polarizers are in complete extinction. It's a very good extinction between those two polarizers. So if I was to remove the sample and look in there, I would see basically nothing. So this is a heterodyne experiment in the sense that we're mixing light generated by the square fluorimeter cuvette itself with the scattered light, and we'll expect for that reason to have a very low optical coherence factor, apparent optical coherence factor. So I'm going to restart this. Let's kill the lights first in this room. And I think that's okay. And we'll start the correlation function. And it does a little bit of auto scaling first. And you see immediately that there's signal, but look, it's only barely above the baseline. Look at your y-axis here, 0.002. Because we have pretty high photon count rates, we were actually able to acquire signals pretty quickly, and you can see the decay. But there's some sort of slow baseline drift in this system that we would have to pull out, and that will make the experiment probably would have to be a sum of multiple short runs. The shortest they could be, if our decay time is a millisecond, we could do individual runs of 10 seconds or so, maybe 20 seconds. So, and then you would sum those, and I bet you would wind up using a fitted baseline anyway. Often in these heterodyne experiments, you want a fitted baseline. So, but anyway, the signal is immediately available. And we'll let it run for a little while. And you'll see that it's noisy at the beginning. That's due to photon starvation. There just aren't that many photons per measurement sample at the early times. And then at the end, it's kind of noisy and bumpy because the system is still settling in. And it takes, for that lag time there of 10,000 milliseconds, 1 E4 is about where it is now. So that's making comparisons of 10 seconds. To really get the response of the system at those times, you would need exceedingly long acquisition times. So I think what we'll do in practice is let this guy run for a little while and then try to fit the baselines. I wonder how this system looks in other representations. Let's just see what it looks like if we go to a linear x. Yeah, it's much more like an exponential decay in that sort of system, right? So I could come out here and fit a baseline, or just take that as the baseline, and fit the rest of this. And I think if you're experienced at looking at these things, you will say this just doesn't look like a monodispersed system. And that's what we're thinking about doing with this particular experiment, is using this as a sort of a budget version of this to characterize cellulose nanocrystal distributions, size distributions. I think what we would probably want here is a longer cell, so the sample has to go through a longer path, or the light has to go through a longer path. That will give us more signal over the leaked light from the cell. And we probably would go to actually a less expensive cell. Flimeter cuvettes that we're using now are kind of tend to be birefringent like that. They have other attributes, but they are not particularly stress-free. So that is a depolarized zero-angle light scattering experiment in a nutshell. Let's go back to our time axis here and see how we're doing. Yeah, I bet I could get something out of that. And anybody who, like I say, who's looked at a lot of these would say, oh my goodness, this is containing a lot of different sizes. And the depolarized dynamic light scattering experiment is very sensitive to size distributions. So this might be a pretty good way in a biorefinery or some similar type operation to characterize the quality of the product. Okay, that's all we'll say about this for now.